And this is Lab 3 for Physics 2212, the magnetic field of a bar magnet. In this experiment, we measured and modeled the magnetic field of a bar magnet using the distance dependence of the magnetic field due to it. These measurements allowed us to make observations about the relationship between distance and magnitude of the magnetic field. We used this relationship, obtained physical values derived from the distance dependence equation for the magnetic field, and applied it to the Biot-Savart law to calculate the magnetic dipole formed by the bar magnet. After conducting the experiment, we obtained results of n equals negative 3.0937 meters and our magnetic dipole equal to 1.56 amps times meters squared. Some relevant physics principles utilized were the Biot-Savart law, which explains the production of a magnetic field produced by a stable electric current. We applied the concept of superposition of the magnetic field of the bar magnet onto Earth's magnetic field. We utilized the magnetic dipole as a vector quantity used to measure the tendency of an object to interact with an external magnetic field. The distance dependence equations according to the Biot-Savart law and relationship between distance and magnitude were utilized to calculate values for K and therefore the magnetic dipole. And finally, we used the equation for the magnetic field of a dipole to calculate the off-axis magnetic fields, which were then translated into our GlowScript code. To obtain the data for this lab, a magnetometer was utilized on a smartphone device to obtain measurements for the magnetic field both on and off-axis. The values for average distance and average magnetic field for the on-axis values were linearized and plotted on the graph to the right, yielding the equation for the line of best fit. Before moving on to the calculations obtained for this lab, let's discuss some observations experienced during the procedure. An inverse relationship between magnetometer distance from the magnet and magnitude of the x component of the magnetic field was observed. In other words, as the magnetometer moved closer to the magnet, the x component of the magnetic field increased and vice versa. And once the magnetometer was far enough away from the magnetic field in the x direction eventually became near zero. To carry out the calculations for this lab, the equation generated for the distance dependence was utilized. I derived the values for ln, k, and n from the graph as the y-intercept and slope for the line of best fit, respectively. I then applied the inverse logarithmic function to obtain a value for k. I plugged all the obtained values stated on the previous page into the equation for the magnetic moment and solved for mu, or the magnetic dipole. Once carried out, we can obtain a value for the magnetic dipole as equal to 1.56 amps times meters squared. The code is centered around creating a function for the magnetic field as previously derived from the Biot-Savart law. This described what a magnetic field would be due to a dipole at a particular location. After coding the function, I plugged in the calculated value for mu of 1.56 amps times meters squared into the code. I then coded 2 axis locations as well as 4 perpendicular locations of the magnetic field using arrows of different colors. The magnitude of the magnetic field will be calculated at each of these 4 locations once the code is run. To create the magnetic field 45 degrees off-axis, I inputted the average d perpendicular value location as derived from our magnetometer measurements, which was the value of 0.182 meters. I then coded the calculated magnetic field for that given location using the obtained values from the magnetometer. The model generated demonstrated the magnetic fields on-axis with orange arrows, perpendicular with cyan arrows, and 45 degrees off-axis with the green arrow. To the right demonstrates the magnetic fields generated on the axis at all 7 locations as printed by the code after running the model. The code also calculated for d, or the magnitude of the recorded value for the average d perpendicular. If we had not oriented our experiment to compensate for magnetic north, the results determined would not have been as accurate, as there would have been no way to ensure that our calculations for magnetic field started at 0t. By orienting this experiment at magnetic north, the Earth and magnetic field are perpendicular, and the bar magnet's magnetic field can be superposed onto Earth's, creating a net magnetic field that is equal to only the bar's magnetic field contributed. If 2 identical magnets were stuck together end to end and the experiment were run again, the strength of the magnet would increase, and therefore the magnetic field calculated would also increase due to this strength. In a perfect scenario, the value would hypothetically double to account for a twice as strong magnet, but the magnetic field calculated may not be completely doubled due to outside circumstances.